Hello all, welcome to my course on methods of adhesion measurement, theory and practice, and we are going through the very interesting surface science and adhesion science and surface energy and interfacial energy estimation and like that. So, today we will continue that discussion. In the last lectures, I described to you the interaction energy between two materials 1 and 2 which are immersed in a medium 3. So, the interaction energy delta F 132 LW Lipschitz van der Waals component, that is given by this equation, and then we have this. So, if we analyze this equation to state that when there will be attraction between these materials 1 and 2 which are both in medium 3 and when there will be repulsion, and we also talked about few special cases, and we also described or presented this Young's equation which we have not yet proved, we will prove that, and then we have also presented this good Grey-Falco equation, and we have said that this gamma SL can be written in terms of these quantities on this good Grey-Falco equation, and both the equation can be combined to write or this particular equation, and this is called the Young-Dupree equation. And these three equations are very useful practically in solving problems in practical applications in which you need to know the surface energy of a material or the interfacial energy between two materials. Okay. These three equations are very useful, and we have also presented a few examples, and in if you are working on with this kind of materials and their adhesion or weighting, okay, you will be using these equations often. So, today I will like to continue the discussion that was going on. So, let us say that we have talked about this delta F 1 to the Lipschitz van der Waals component, but what happens is that there are polar component also, that also I discussed, and we talked about this polar component of the surface energy, and the polar component surface energy I did not write any expression, but I said that when you talked about the total surface energy of a material, let us say gamma 1 LW and gamma P, that will be the total surface energy, that I have said. Now, I did not give any specific form of the polar component. The polar component can be given something like this. So, here this part you see that this defines the interaction between the electron acceptor atom of species 1 with the electron donor or donor part of species 2. So, gamma 1 plus, okay, should interact with gamma 2 plus here, gamma 2 minus here, and gamma 1 minus here should interact with gamma 2 plus. So, what it means that gamma 1 P that has got can be divided into 2. So, gamma 1 plus and gamma 1 minus, and when they interact, then to find out the polar component of the interfacial energy, then you have to take this gamma 1 plus interacting with gamma 2 minus, gamma 2 minus and gamma 2 plus, and like that. So, that is the way calculation has to be done. So, I will demonstrate here. So, for example, let us say for water. So, for water, let us say this quantity gamma 1 plus and gamma 1 minus, both are 25.5 millijoule per meter square, and so gamma 1 P will be actually equal to 2 into square root of, let us say 25.5 into 25.5, because it is same material. So, it will be like that. So, therefore, this will be equal to 51 millijoule per meter square. So, for pure component you take only one of this, because that is what you have, and so it is gamma 1 P will be 2 into square root of 25.5 into 21.5. So, gamma 1 plus is a polar component, and then the total polar component comes out to be 51 millijoule per meter square. So, these are all in millijoule per meter square, these quantities are all in millijoule per meter square. Similarly, for let us say ethylene glycol, okay, you have to multiply 1.92 into 47 and square root into 2, and that will you will get here 19 here or like that. So, that is the way this polar component of the surface energy that is estimated. So, you may ask that how do I get this polar components separately, gamma I plus and gamma I minus. So, see, when you determine when you have to determine like that, you have to remember then you have got 3 unknowns, gamma y 1 LW, gamma I plus and gamma I minus. So, they have got 3 unknowns. So, you will require 3 equations. So, in the last lecture I was describing you that how to determine gamma I LW and gamma I P. I did not divide this P into these separate components. So, if I have to do that, then I have to have 3 unknowns, and so therefore 3 equations. So, what it means that suppose you want to find out the Lipschitz Van der Waals component and then gamma I plus and gamma I minus for a given surface, then in order to find out these 3 unknowns, you will require 3 different liquids in order to find out these 3 unknowns. So, you have to write that equation, this equation over here. Okay. So, here instead of this you will have also you will have to write here instead of this term you have to write here gamma S, and let us say this is plus gamma liquid minus, and plus you have to write here square root gamma S minus and gamma L plus. Okay. And so, there will be 3 unknowns now, gamma S plus and gamma S minus and gamma S LW. So, you have to use 3 liquids for which this gamma L LW is known, gamma L minus is known and gamma L plus is known. All these 3 things are known, and then you will solve simultaneously these 3 equations to obtain for this solid gamma S plus, gamma S minus and gamma S LW. But normally for most cases it will be good enough to consider only gamma SP as a total polar component. So, I will like to now show you an experiment, okay, which is done actually in the laboratory to see that, and then go through the calculation to show that how to estimate this interfacial energies, or let us say the surface energy, estimate the surface energy of a solid surface. So, we do not know the surface energy of the solid. So, how to estimate that? So, let us say this surface is a glass surface that is coated with a certain hydrophobic molecule. So, you know that the glass has got SiOH groups. So, glass is actually hydrophilic, pure glass that is actually hydrophilic. Okay. But then I can make some coating on this surface. So, the coated molecules actually look like something like this. So, let us say this is Si here, this is Cl here, this is Cl here, this is Cl here. This particular chain is just alkane chain. Let us say this is C18. So, that means 18 carbon CH2 groups and CH3 groups are there, and so this particular molecule is called octadecyl trichlorosilane, octadecyl trichlorosilane, octadecyl trichlorosilane. This particular molecule is called. Now, this particular molecule can be chemisorbed into the glass surface. So, it forms a monomolecular layer like this, self assembled monolayer we call it, and therefore, when you put a drop of water on this surface, this drop of water does not see the bottom surface over here, that is the SiOH groups and all that. It sees only these chains, okay, and these are all non-polar groups, CH2 groups and CH3 groups and like that. So, therefore, this surface behaves as a hydrophobic material. So, now we will put this, so we want to find out that what is the surface energy, okay, of this hydrophobic glass plate, that is what we will do. So, the experiment is done here something like this. So, here we have a glass plate here. So, this is the glass plate, that is that coated with that monomolecular layer of that OTS molecules. This is a camera here. By using this micropipette, the drop is dispensed. So, here a drop of water is dispensed first, and then there is another drop of water liquid. So, you need to, so in order to find out the surface energy, you need actually 2 different liquids. So, that is what had been done. So, here so this is all done on a optical table, so that there is no vibration as such. The vibration that you are seeing because the camera is handheld, that is why little vibration is there. But now we will see the microscopic picture of this. So, let us say that so these are the let us say that this is the picture of that particular drop. So, that was let us say water here, this is water, and then there is hexadecane or pentadecane that will also be put, So, yeah. So, this is a another liquid. So, this is hexadecane I guess, and yeah. So, you will see that it completely spreads, okay, spreads not completely, at least to a large extent. So, what we do is that we find out now the contact angle. Okay. So, this hexadecane is used. So, contact angle of this liquid on this two on the same glass surface. So, you see that the glass slide, okay, having this monolayer that allows these two liquids to spread to different extent on this surface. So, here, so first of all you have to see the contact angle. So, you see when you find out the contact angle, you should always measure a few different droplets and get the average value. So, here I will do the average of this 103.3 plus 102.6. So, that will come out to be 102 point, let us say close to 103, let us say 103 here, and let us say 31.6, and the average will be let us say 30. So, it was 32.3 here, let us say 32.1 here, like that. How much I got here? 32.2 here and 103 here, let us say 32.2, okay, 32.2 here, like this. And then we use that equation here, Young-Draper equation. So, Young-Draper equation is like this. So, here 72.8, gamma L is 72. So, water here, so it is 72.8 into 1 plus, so it is 103. So, cos of 103 here is equal to 2 into and square root of. So, this is 21.8 gamma L water and dispersive component 21.8 into gamma 2 we do not know. So, that is gamma S and dispersive component or LW. I told you that I can I will use this interchangeably, this D and LW. So, this is basically the dispersive or least van der Waals component, same thing, and here gamma 1 p is 51 here into again gamma S p, that is unknown, that we need to find out. So, there are two unknowns here, and over here I have let us say hexadecane. So, hexadecane has the total surface energy is about 27.48, here it is 72, gamma water, okay, it is 72.8 millijoule per meter square here, millijoule per meter square, it is millijoule per meter square here. So, here we write here 27.48 into 1 plus cos, and this is angle was 32.2. So, let us say 32.2 here is equal to 2 into, here it is square root of, this is 27.47, 27.47 into gamma S, gamma S D plus this is 51, this was 0 here almost. So, let us take 0, okay, let us not worry about it, let us take 0 here, 0.0 and very close to 0. So, this is gamma, this is S, I should write, this is S, right, it is P here like this. So, here you see there is an advantage of taking a liquid whose polar component will be almost equal to 0. So, it simplifies to some extent our calculation. So, then I can, now we have these two equations with two unknowns, okay, and we can easily solve it, these two equations, and we can show that this gamma SD and gamma SP comes out to be like this 23.27 here, 0.64 millijoule per meter square, and overall gives 23.91. So, it says, so you see the polar component of this surface is indeed very low with respect to the dispersive component. So, naturally the water droplet, that water has got a very high polar component of this surface energy, that is 51. So, it does not interact much, cannot interact much with this surface, and so therefore, it attains a very high contact angle, right. So, that is the way you can use this method to measure the surface energy, okay, and in fact two different components, the dispersive component and the polar component of the surface energy in this method. So, this was quite nice and is quite useful, and people use it quite often. And now, I will show you the second problem in which we like to find out the surface energy of a liquid, okay, whose surface energy is not known, we like to find out that. In that case, we will use two different solid surfaces. So, here for example, this is I guess hexadecane or hexane, which is being placed on two different liquid surfaces. So, in one surface this forms it spreads almost to quite a lot, and then there will be another surface on which it will on which it will spread only partially. So, right. So, now you see that the contact angle on these two surfaces are different. So, the surface is actually material wise it is same, but what has happened is we have made this surface different by attaching different or chemically changing the surface. So, for example, here it is hydrophobic glass slide. This is, as I said, those alkane group chains which are attached to the surface. So, hydrophobic glass slide I just described in the last few slides ago, and here the same glass slide has been coated with some oleophobic molecule. That is also possible, and therefore, this oil hexadecane that forms a finite contact angle which is larger, which is not exactly 90 degree or like that, but it is still quite high, 65 or 64 degrees Celsius, 64 degree. So, it is average will be 64.5 degree here, and here it will be 32.7 or so, like that, 32.75 or like that. Now, here we have these two different contact angles, two different surfaces, but the same material, that is hexadecane. So, let us say we do not know the hexadecane's surface energies. So, again we will use the same method that we described earlier. So, here we will have the hydrophobic glass slide which has a surface energy of 23.27 and 0.64. So, we just determine that, and similarly this hydrophobic glass slide, that also let us say we have determined by a method that I used to determine this, the same method, same method, but then the method we have used, and we can get here 14 and 1.96 milliliter per meter square, and then we use these two values over here. So, here one is the hexadecane and the two is either this is the hydrophobic glass slide or let us say oleophobic glass slides. So, now you put these values over here. So, gamma L, so gamma 1 is hexadecane, right. So, hexadecane, right. So, hexadecane is let us say gamma 1. So, gamma 1 is the unknown, right. So, this is let us say gamma 1, I will write it as gamma 1 d plus gamma 1 p, because these two components I want to find out, 1 plus cos of theta. So, theta value here is 32.7, let us say 32.7, and that is equal to 2 square root of. So, here is gamma 1 d is again unknown. So, gamma 1 d, this is unknown, actually not such big, I need a smaller one. So, gamma 1 d unknown, gamma 2 d, let us say it is the hydrophobic glass slides, that is 23.27 plus this is let me write over here, not much space here. So, here let us say it is gamma 1 p into, now it is 23.2, so it is 0.64, this 0.64, 0.64 over here. So, this is forms one equation, and the second equation again it will be the same. So, here again it will be gamma 1 d plus gamma 1 p here into 1 plus cos of, here the angle is 64.5. So, it is 64.5 here, and that will be equal to 2 into, here it will be square root of, this is gamma 1 d and into 23.27, no, here it is 14. Here the dispersive component of this oleophobic glass plate that I have to put. So, that is 14 here plus this is gamma 1 p here into, this is 1.96. So, it is 1.96 here. So, these are the two equations. Now, that needs to be solved, and here two unknowns are there. So, it can be solved and we can find out these values again. Here it is written the same thing, and it can be found out. I have not found out the solution, you can possibly do that. It is now found out. This is 27.6 here, and I have found out to be 0.0. So, hexadecane is expected to have very small value of this polar component anyway. So, this is very small. So, here like that. So, this method that I have showed you, that is useful for finding out the surface energy of a liquid or of a solid surface, and it can be done easily. Now, I will like to go about finding out some manifestations of surface energy liquid. Now, we are talking about surface energy liquid, where do we see this? So, actually we see surface expressions or manifestations of surface energy liquid in many different forms. For example, a droplet on a lotus leaf, it forms this beautiful spherical liquid drop because liquid wants to minimize its surface area. So, it wants to form a sphere, sphere is the minimum surface area per unit volume. So, it forms a liquid drop here, we see this, or we can also see in a faucet the liquid water that falls, and after some time it breaks into small drops. Okay, that also happens because of surface tension, unstable this particular liquid jet that becomes unstable and it breaks up into liquid drops like that. This is called Rayleigh Plateau instability. We can see the manifestation of surface tension there. Here also capillary rise. So, you take a thin capillary hydrophilic, let us say, and you put it inside this pool of water, let us say, and you will see that the liquid that rises to some height. Why does it do that? Okay. So, this is called the capillary rise, and this also is driven by surface tension. Okay. It is a surface tension of the liquid air interface or liquid vacuum interface. So, that drives this this effect. So, this is called the capillary rise. Then we also see some other examples. This is in fact exotic examples. So, here this is called water walking insect. So, as far as the bulk density is concerned, this insect will definitely have bulk density larger than water, but then it can walk on this particular surface because this feet of this insect, it has got fine hairs. So, the water, there is a meniscus that form between these hairs, and that meniscus give rise to surface tension forces, and we can see this effect of again water surface energy. Now, I have talked about measuring the surface energy by using this Good-Girifalv equation or the Young-Dupre equation, but we can also measure it directly by other means. So, essentially by using the principles, using the manifestations of surface energy in all these cases. So, it can be measured. I am not going to go into detail that how exactly these different methods work, but I have to just present that these are different methods by which surface energy of a liquid can be measured. So, for example, here this is called a pendant drop method, in which you have got a needle, you push little bit of liquid. So, you measure what is the pressure difference, and by that what is the kind of diameter, volume, etc. we get, and there are beautiful goniometers and equipments available. You can actually measure it, directly gives you the surface tension. Similarly, you have got this Wilhelmy plate, this is called. So, in that case you have a solid surface on which let us say the liquid completely wets, let us say the theta is very close to 0, and now you try to pull it. So, when you try to pull it, okay, gravity of course is one aspect that you have to take care of, but then the surface tension of the liquid tries to pull it down because of this meniscus. So, you can balance the amount of force that is required to pull this plate and the surface tension. You can show, you can calculate, and you can estimate the surface tension of the liquid here like that. This is called this Wilhelmy plate method, that is used a lot. Then the capillary rise, as I was describing. So, the capillary rise over here, this it can rise because of the pressure difference across this interface. Can you imagine? Because of the pressure difference across this interface, okay, we can show that the liquid rises to some to that extent. So, we know how to relate this pressure difference across this interface, okay, by using the surface tension, which is called the Laplace pressure, and then we can relate it to this capillary, this height, this hydrostatic pressure that is over here, and that will give us an estimate of the surface. But you have to make sure that we have to measure correctly this contact angle here, or you have to make sure that we use a capillary within which the liquid wets completely. And this particular method, which is called the Du-Noy ring method, that is very similar to the this Wilhelmy plate. So, in that case there is a ring there and a meniscus is formed over here, and this meniscus gives pressure. You can calculate what should be this meniscus force, and that is the force that is required to pull this ring up from this particular liquid, and that way also you can measure the surface tension. There are other methods as well to measure the surface tension of liquid, but these are some of the common, and if you want to know more about it, look for some literature or some books, you can get it. Now, I will like to give you some idea, some another concept I will like to bring up, and this is about surface tension. So far remember that I am talking about surface energy, but what is surface tension, and I will to put it in a not a very elaborate manner, but to some briefly over here. So, for example, here let us say this is gamma L. So, gamma L is the surface energy of this liquid surface, this gamma S is this surface energy solid in contact with air. So, this is air here, let us say this is let us say the liquid here, and this is the solid here. So, this is the solid here. So, the solid has got surface energy here, this is gamma SL. So, gamma S is the interfacial energy between solid and liquid. So, the question is that what kind of contact angle or how much it will spread, okay? How much this particular liquid will spread, okay? How this equilibrium of this of equilibrium contact angle that is reached, that is the question. And you know that when we talk about equilibrium in thermodynamics, we talk about the minimization of the energy, okay? That is what we talk about. So, here I will not very rigorously, but show you that minimization of the energy, total energy indeed gives rise to this minimize the equilibrium contact angle. So, for example, here what is the total energy of this system? So, we can write it gamma L into AL, that is the energy corresponding to this particular surface. Then I can write gamma SL ASL, that is corresponds to this energy, and then I have gamma S into AT minus ASL, because this the gamma AT is the total surface energy, the total surface some portion is taken occupied by this liquid. So, that portion is ASL, rest is AT minus ASL, and the total energy we multiplied by gamma S into this quantity, and this is the total energy. And so, now we can minimize this and we can find out that what should be the equilibrium contact angle. So, I will take up the derivation of that equilibrium contact angle in the next lecture. Thank you for your kind attention.